Okay, so we have a guy that's crouching, about to jump off this scale. Okay, remember the scale reading is equal to the normal force. The force of the scale pushing up the guy against the guy's feet. So what happens is he's accelerating off the scale. So when he's just resting, like in that picture right there, the weight is equal to the normal force. Okay, so that's what we start out. The scale reads the weight. But then he accelerates off of it. To accelerate off of it, he has to push against the scale. And the normal force has to be greater than the weight. So what happens is the weight greatly increases depending on how hard he jumps off of it. And then as his feet gradually come off the scale, the weight decreases until he's off the scale, so it decreases to 0. Now, when I say the weight, what the normal force is. So his apparent weight decreases to 0. His true weight is not even affected, obviously. So once again, when he's just about to jump, hasn't pushed against it yet, the normal force equals his weight. And then as he pushes against it, the normal force becomes greater than his actual weight. And then as he comes off the scale, that normal force decreases to 0. So when I say the weight, it's really the normal force. Okay? So next one. A force of 5 newtons increase the box from a rate of 1 to 3 with what change would make likely. Okay, so 5 newtons. So look at this equation. Net force equals ma. So we have a box like this. We got the weight. We got the normal force. It didn't say anything about friction, but let's just assume there isn't any friction. So here's the force of 5 newtons. Okay? What change would mostly require additional force? Well, think about it. I think of the second law. So they want for the same acceleration. If I want the same acceleration, and I increase the mass? Well, what would I have to do to the net force? I'd have to increase the net force proportionally. So, or if there was friction on it, and I wanted the same acceleration, let's say there's friction, I'd have to increase the force applied as well. Okay, so let's look at choices. Make the surface of the box smooth. Well, that would probably decrease the friction. I'm guessing. I don't know. Reduce the mass of the box. No, that would decrease the force needed. Increase the mass of the box. That's the answer. Make the floor smooth. Well, that's the same as that. Make it easier to less friction. Okay, so if the mass or the friction increases, I'd have to increase the net force. Okay, this one, mass is 10 kilograms. Let's do a free body diagram. Here's Akbar, force of A equals 50 newtons. And the force of Lucia, I don't know what that is. That's what I'm looking for. The car accelerates towards Akbar. So since the acceleration is that way, I know that Lucia is pushing harder than Akbar. Where do you get these names? So also because the acceleration is to the left, net force is to the left, and so FL has to be bigger than FA. So the net force is mass times acceleration, so M times A. So we got 10 times 2 equals the CS force minus Akbar's force. So Lucia is pushing with a force of 70 newtons. Hot air balloon lifting. So there's a lifting force of 12,000 newtons pointing up. There's only one that points up. It's pretty easy. And then the weight is 800 newtons pointing down. So that's the correct choice. Probe travels around moving at constant velocity. Well, if you're moving at constant velocity, acceleration equals 0. Net force equals 0 as well. All the forces are balanced. So as I was saying, if you're moving constant velocity, the acceleration is 0, the net force is 0. That means there's no unbalanced forces acting on you. So let's see. An unbalanced force is acting on the probe, causing it to accelerate. No, it's not accelerating. It's going constant velocity. So that's not it. Letter B, the probe will continue on its current path until an unbalanced force acts on it. Well, that's the first law of motion, so that is it. It will continue going with constant velocity until a net force acts on it. Okay, let's go to number 6. Which statement best describes what must happen in order for a person to lift an object? Well, to lift an object, you have to have an acceleration upward if it's at rest. Okay, and then the net force has to be up as well. So you got to apply force upward greater than the weight downward. The weight is called the force of gravity. So it has to be that choice. Now, if it's being lifted up at a constant speed, well, then there is no net force. And the lifting force, I call that the applied force, can be equal to the weight once it's moving. Okay, let's look at number 7. Diagram force on it. Like, okay, so I have the acceleration, no friction. What's the mass of the block? Okay, well, the net force, I'm assuming the normal force and the weight are constant. Are equal because there's no unbalanced vertical force. So this would be the bigger minus the smaller. And that would be, 12? And then F net is also equal to MA, second law of motion. M is what I'm looking for, but the acceleration is 6. So we're looking at the mass being 12 divided by 6, or 2 kilograms. Okay, 2,000 cars pulling. Okay, this looks complicated, but it's easy. So if I make the car and trailer a system, I got 6,000 newtons that way. And I got 1,000 and another 1,000 that way. I'm not drawing them the right sizes, but so what's the net force? Well, this 6,000 would be way over here somewhere, right? If I were to scale this somewhat properly. Okay, so net force is the bigger one minus the sum of the smaller ones, so 6,000 minus 2,000. That comes out to 4,000 newtons to the left. So I should have said to the left. Okay, number 10, ball mass, initial velocity. The ball is given acceleration. What is the net force? Okay, there's a lot of extra stuff here. But the net force is simply second law of motion, the law of acceleration, the mass, which is given as 0.1, times the acceleration, which is given as 30. So that comes out to 3 newtons. Number 10, diagram below, box sliding across at constant speed. Okay, constant speed, that means the acceleration is 0. That means there's no unbalanced forces. Okay, so if there's no unbalanced forces, the friction has to balance out the applied force. Here's the normal force, here's the weight. So the friction has to balance out the applied force. So that would be 1.7 newtons to the left. But they just said, what's the magnitude? Okay, is that it? Yeah, okay.